Hello. In this final video from Chapter 13, I'd like to talk about Le Chatelier's principle. And Le Chatelier's principle deals with the question as follows. Suppose I have a system at equilibrium. Everything's nice and happy. And then I start messing with it. I impose some change. What will it do in response? Well, Le Chatelier's principle says that if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change, meaning the reaction will either shift toward the forward direction or toward the reverse direction in order to minimize the effect of the change that you imposed. And here are the possible changes we're going to consider. Change in concentration of a reactant or product, change in pressure if it's a gas phase reaction, change in temperature, and addition of a catalyst. So the skill then is, given a system at equilibrium, a particular chemical equation at equilibrium, and a specified change, predict whether the system will shift towards the reactants or products in order to reestablish equilibrium. And again, keep in mind that the fundamental principle is the system shifts in the direction that tends to minimize the effect of that change. So let's talk first about a change in concentration. So let's consider a system at equilibrium. We've got nitrogen, hydrogen, and ammonia, and these represent equilibrium concentrations. Clearly, this is the ammonia synthesis reaction. N2 gas plus 3H2 gas in equilibrium with 2NH3 gas. Yes, I'm sick to bloody death of it as well, but the fact is that a lot of what we know about equilibrium was determined by studying this reaction. Okay, so let's take these equilibrium concentrations, write out our equilibrium expression, and calculate the equilibrium constant at this temperature. So 0.202 molar ammonia squared over 0.399 molar times 1.197 molar cubed gives me a value of 0.0596 at this particular temperature. So what will happen if, to this equilibrium system, I increase the concentration of N2, a reactant, by 1.00 mole per liter at constant temperature? Okay? Well, I will now have a new set of initial concentrations, which are now 1.399 molar for hydrogen, 1.197, hydrogen is 1.197 molar, and ammonia is 0.202 molar. Notice that these initial concentrations, hydrogen and ammonia, are initially the same, but the concentration of nitrogen has increased by 1 molar. Well, we dealt with this in an earlier video. If you have a set of initial concentrations and you don't know whether they correspond to an equilibrium position, and more importantly, in which direction the system must shift in order to reestablish equilibrium, we're going to calculate the reaction quotient Q. So Q then will be the concentration of ammonia, pardon me, that should be squared, not cubed, divided by the concentration of nitrogen times the concentration of hydrogen cubed. That gives me a value of 0.0170, which is less than K. And because Q is less than K, we would predict that we would shift toward the products in order to increase the concentration of products and decrease the concentration of reactants. And that makes sense because the stress we placed on the system at equilibrium was to add excess reactant. So to minimize the effect of that stress, it will shift in such a direction as to use up that reactant, which is in the forward direction. So let's generalize. If a component is added to a system at equilibrium, the equilibrium position will shift in the direction that lowers the concentration of that component to use up the excess stuff you put in. If the component is removed, the opposite effect occurs. Okay? So if I have A in equilibrium with B, and I want to predict what's going to happen with each particular change, if I add a reactant, it will shift towards the product to use up that excess A. If I add B, a product, it will shift to the reactants to consume it. If I remove A, in order to make up for the missing A, it will shift towards the reactants. And if I remove B, it will shift towards the products to make up for the lost B. Pretty straightforward. Now, let's talk about a change in pressure. There are three ways to change the pressure of a reaction system that involves gaseous components. One would be to add or remove a gaseous reactant or product. The other would be to add an inert gas, that is a gas that's not involved in the chemical equilibrium. And the third would be to change the volume of the container. So let's consider each of those successively. Okay? Let's consider adding or removing a gaseous reactant or product. Well, we just talked about that. The system shifts in whichever direction it needs to either consume the excess stuff you added or to replace the stuff you took away. What about B? Adding an inert gas, that is one that doesn't appear in equilibrium. Okay? That would have no effect. Okay? Adding an inert gas would increase the total pressure of the system, but it would not affect the partial pressure of each individual components. No change in Q, so no shift. Okay? Well, what happens when we have a system at equilibrium in the gas phase and we decrease the volume? Well, once again, let's consider our friend the ammonia synthesis reaction. Okay? We've got 1 mole of nitrogen and 3 moles of hydrogen in equilibrium with 2 moles of ammonia. What would happen if the volume of the system is suddenly decreased by a factor of 2? We cut the volume in half. Well, what property changes when we change the volume at constant temperature? Well, if volume decreases by a factor of 2, that must mean the total pressure must increase by a factor of 2. And in fact, the partial pressures of each component would double under these circumstances. So let's ask the question, how will that affect the equilibrium position? Okay, so Kp is the partial pressure of ammonia squared divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. Let's calculate Q. Well, if I take the system at equilibrium and suddenly decrease the volume by a factor of 2, as I said before, I will double all of the partial pressures. So this will become 2 times the initial partial pressure of ammonia squared divided by 2 times the initial partial pressure of nitrogen divided by 2 times the initial partial pressure of hydrogen cubed, which is equal to Kp times 2 squared over 2 to the 4th, which is equal to 1/4 Kp, which is equal to Q, okay? And since now Q is less than Kp, that means we will shift to the products. Will that always be the case? No. In this case, let's look at our coefficients. We have 4 moles of gaseous reactants and only 2 moles of gaseous products. It seems that if we are increasing the pressure, we are shifting towards the side that has fewer moles of gas. And that makes sense. If our stress is suddenly the pressure is too high, and Le Chatelier's principle says we shift in a direction to minimize the effect of that stress, it's going to move in the direction which has fewer moles of gas. So here's our general rule for predicting what's going to happen. If the total pressure is increased by decreasing the volume, the system will shift to the side that has fewer moles of gas to make up for that increased pressure. On the other hand, if the total pressure is decreased by increasing the volume, the system will shift to the side that has more moles of gas to make up for that lost pressure. What if the total moles of gaseous reactants are equal to the total moles of gaseous products? Then there's no shift. Temperature. Why would a change in temperature affect the equilibrium position? Well, I may not have made this clear enough earlier in the unit, but I'll state it now, because the value of the equilibrium constant depends upon temperature. Probably in the first video I said that K for a given reaction is a constant and has a constant value at a particular temperature, but if you change the temperature, you change the value of K. It could either go up or go down. Okay? How does K depend upon temperature? Wait until chapter 17. But for now, let us assume that a change in temperature involves either adding or removing heat energy. If we increase the temperature, we're adding heat energy to the system. If we decrease the temperature, we're removing heat energy from the system. Okay? So let's just consider heat energy to be a component of the reaction, either a reactant or product. Okay? If the reaction is endothermic, that means heat is a reactant, whereas if the reaction is exothermic, heat is a product. So we will simply add heat energy on either side of the arrow. Okay? So let's consider the ammonia synthesis reaction. Okay? Delta H is negative 92 kilojoules, which means we are going to write the equation as 1 mole of nitrogen gas plus 3 moles of hydrogen gas are in equilibrium with 2 moles of ammonia gas and 92 kilojoules of heat energy as the other product. So if we increase the temperature, we add heat energy. That's a product, so that means in order to minimize the effect of that stress of excess heat energy, it is going to shift to reactants in order to use up that excess heat energy. On the other hand, if we decrease temperature, we are removing heat energy. So in order to make up for that stress, it's going to shift to products to create more heat energy to make up for that which was taken away when you decrease the temperature. So, summary of the temperature effect. For an endothermic reaction, for which delta H is positive and heat is a reactant, increasing temperature shifts the equilibrium towards the products to use up the excess heat. Decreasing temperature shifts the equilibrium towards the reactants to make up for the lost heat. On the other hand, for an exothermic reaction, in which delta H is negative and heat is considered to be a product of the reaction, increasing temperature shifts the equilibrium towards the reactants to use up the excess heat, and decreasing the temperature shifts the equilibrium towards the products to replace the lost heat. Finally, let's ask, what effect does the addition of a catalyst have on the equilibrium position? Well, let's review, what is a catalyst? A catalyst is a substance that accelerates a reaction, that is, it speeds it up by providing an alternative mechanism or pathway that has a lower activation energy. Okay? It increases the rate at which the system reaches equilibrium, but once you're at equilibrium, which we are, it accelerates the forward and reverse reactions by the same amount. So, a catalyst has no effect on the position of equilibrium. It will only help you achieve equilibrium faster if you're not already there. So let's do an example. Here we have an equilibrium, and we ask the question, what will happen to the number of moles of sulfur trioxide in equilibrium with SO2 and O2 in the following reaction, for which delta H is positive 197 kilojoules per mole. Okay. So in part A, we add oxygen gas. Oxygen gas is a product. Adding a product causes the system to shift toward the reactants, which means that the moles of SO3 will increase because we're shifting towards the reactants. The pressure is increased by decreasing the volume of the reaction container. We said that if we increase the pressure of a gas phase reaction by decreasing the volume, it will shift to the side that has the fewer number of moles of gas to accommodate that increased pressure. As it is written, 2 moles of gas are in equilibrium with 3 moles of gas. There are fewer moles of gas on the reactant side, so this would also cause the number of moles of SO3 to increase. C, the pressure is increased by adding argon gas. Well, the total pressure would increase, but the partial pressures of each of the components in the equilibrium would remain the same, so there will be no change. The temperature is decreased. Okay. In this particular case, delta H is positive. It's an endothermic reaction, which means heat is considered to be a reactant. If I lower the temperature, I'm removing heat energy from the reactant side. In order to make up for the lost heat energy, we'll have to shift toward the reactants, which means that the moles of sulfur trioxide will increase. Finally, gaseous sulfur dioxide is removed. If I remove a product and therefore lower its concentration, the system will shift in that direction toward the products in order to make up for the lost sulfur dioxide, which means that the moles of sulfur trioxide will decrease. Okay? And that, my friends, is Le Chatelier's principle.